Currently, technology has been continuously developed since the past. Various applications has been developed to be more convenient and responsive to user needs. For instance, mobile phone has evolved from being more communication device to versatile to capable of connecting to the internet. Our current internet signal distribution system uses dual-band technology, which emits both 2.4 GHz and 5 GHz wave. The 2.4 GHz wave can travel up to 60 to 90 meters to its long-range propagation characteristics. However, this long-range capability can lead to bad connection from other users, causing an issue with our device and compromising and privacy of people in the household, potentially exposing a sensitive information like password which could be harmful to our internet user. In light of this challenge, the management has become aware of this problem and has solved a solution by designing and developing the frequency selective surface limit the coverage area of 2.4 GHz wave without affecting the 5 GHz frequency. About frequency 2.4 GHz, the frequency 2.4 GHz has a wavelength about 12.5 cm. About measuring in this project, we use a recessive signal strength indicator, or you can call RSSI, and data rate value. Recessive signal strength indicator is a unit in decibel milliwatt used to measure the signal strength. Our objective is to study the reflection and absorption of electromagnetic wave for limiting the range of frequency 2.4 GHz. The second point is to study the design of frequency selective surface type reflection and absorption. Hypothesis: frequency selective surface can limit the area of frequency 2.4 GHz wave.
Part 1 FSS Preparation. The first part involves preparing the frequency selective surface (FSS). This begins with the design and simulation of the surface material to selectively limit the coverage area of the 2.4 GHz wave. Using CST Studio software to find the dimension that yield the highest reflection efficiency for this 2.4 GHz wave, including the workspace, the dimension that show the highest reflection efficiency are a frame made of copper with width of 0.5 mm and 2.7 mm. The following steps are taken to prepare the FSS. 1. Printing the rectangular frame. Print a rectangular frame with dimension of 26 mm in wide and range on a sticker paper in a 5x5 pattern. 2. Cleansing the PCB. Clean the printed circuit board using fine sandpaper to remove any impurities on the surface. 3. Coating the PCB. Apply lacquer on to the copper coated side of the PCB, ensuring full coverage. Then press the printed sticker paper onto the coat side of the PCB and wait for approximately 15 minutes. Afterward, peel off the sticker paper and immerse the PCB in clean water to remove any remaining sticker residue. 4. Preparing the etching solution. Mix on part etching solution with 3 parts water in a container. Immerse the PCB in the etching solution until the copper part is fully etched away. Rinse the PCB with clean water and remove any ink residue using thinner. Part 2. Antenna preparation. The second part involves preparing the antenna. This is done by shaping the wire into the rectangular fabric-like structure with dimension of 25 cm in wide and 27 cm in range.
Part 3. Preparation of simulation box. In this part, a simulation box is prepared to control and direct the propagation of waves in the desired plane. The box has dimensions of 26 cm in width, 46 cm in length, and 13 cm in height. The box is covered with a mylar film. Then, holes are drilled on the box with dimensions of 14 cm in width and 14 cm in length to allow the waves to propagate out of the box in the desired plane. Part 4. Testing signal power and download speed. The testing process involves 3 scenarios. First, testing without any blocking material. A smartphone is placed inside the simulation box, and the smartphone transmits waves at 2.4 GHz using the hotspot function. The signal power and download speed are measured without any obstructing material. Second, testing with a copper sheet blocking material. A copper sheet is placed to block the signal on the simulation box. The signal power and download speed are measured in this scenario. Third, testing with frequency selective surface as absorbing material. A PCB with a rectangular frame of 2.7 mm in width facing inside the simulation box is placed on the box hole. Then another PCB with a rectangular frame of 0.5 mm in width facing outward is placed on top of the previous PCB. The signal power and download speed are measured in this case.
Testing frequency selective surface type of reflection. Place the rectangular frame PCB with a 2.7 mm wide edge into the slot of the simulation box, with the side containing the copper facing inward toward the simulation box. Then place the antenna on top of the PCB.
Our tests are conducted using the Wi-Fi scanner program to measure signal power and the fast.com website to measure the download speed. The results are recorded, and the same procedure is repeated for the 5 GHz wave, with the outcomes also being recorded.
From the experimental result, it was found that the signal power for both the 2.4 GHz and 5 GHz frequency was approximately minus 31 decibel milliwatt dBm, with a data transfer rate of approximately 11 megabytes per second (Mbps). The surface material with absorbing and reflecting frequency selective characteristics were able to block the transmission signal power from both frequencies. The signal power of the 2.4 GHz wave for the absorbing and reflecting frequency selective surface material was minus 52 dBm and minus 39 dBm, respectively. The corresponding data transfer rate were 1.43 megabytes per second and 4.10 megabytes per second, respectively. During the testing of the 5 GHz frequency, is what occurred that change in signal power and data transfer occurred due to the imperfection in the absorbing frequency selective surface material. Therefore, the signal power affected the data transfer rate, but it did not impact the transmission rate from the device. After passing through both types of frequency selective surface material, the data transfer rate from the device was unstable for the 2.4 GHz wave.
Conclusion. Based on the experimental result of the frequency selective surface, it can be concluded that the absorbing type FSS for the 2.4 GHz wave was the most effective in limiting the coverage area of 2.4 GHz frequencies. This was evident as it could significantly reduce the signal power and data transfer rate for the 2.4 GHz wave. Additionally, it had the least impact on the 5 GHz wave. On the other hand, the reflecting type FSS had the ability to limit the coverage area of the 2.4 GHz wave to some extent, but it has a more pronounced effect on the 5 GHz wave.